Welcome to 4.1 Inverse Functions. So let's just jump right into it. Let's talk about the definition of an inverse function. If the ordered pairs of a function g are the ordered pairs of a function f with the order of the coordinates reversed, meaning the x's and y's are flip-flopped, then g is known as the inverse of f. And the notation we would use, if f of x is the ordered pair xy, then the inverse of f, and if you look closely, that's the notation f to the -1, but we don't say f to the -1, we say f inverse. All we do is we switch the x and y values. So if we look at this first example, and we're given f of x as the set of all these ordered pairs, and I ask you to find f inverse, well, all we're going to do is take these ordered pairs and switch the x and y values. So instead of the 0.12, we now have the 0.21. Instead of -3,5, we have 5, -3. Instead of 12, 0, we have 0, 12. And instead of 0, -7, we have -7, 0. The last thing we want to find now is f inverse of 5. So I look for when the x value of my inverse, is 5. So as you can see, the arrow is pointing to it. This is when the x value is 5, so my answer is the y value. So f inverse of 5 equals -3. Now we have to look for the condition for an inverse function. So a function f has an inverse function if and only if f is a one-to-one function, meaning for each y, there's only one x, okay? For each y, there is only one x. And we're going to talk about the horizontal line test. You should be familiar with the vertical line test, but what does the horizontal line test allow us to find? All right, then the other part is if f is an increasing or a decreasing function, then f has an inverse, okay? So we can think about that as well, but again, it all comes down to this horizontal line test, all right? And so we can take a look at a function to determine if its inverse is a function using the horizontal line test. So let's look at these two examples here. Which of the following functions graphed below has an inverse function? So imagine holding a horizontal line, okay? And what we want to do is we want to see if this horizontal line only passes our graph at one point, meaning for each y, there is only one x. All right, so what we should see is, yes, this one does pass the horizontal line test. So it is, the inverse is a function. So how would we write that? So if we look closer, we can see the inverse is a function because, well, one, our function is increasing, meaning going from left to right, the y values continue to increase the entire time. They get bigger and bigger. So it's increasing the entire time. It's also one-to-one, meaning for each y value, there is only one x value. So that tells us that it passes the horizontal line test, HLT for short. Let's take a look at the second example. So let's look at B. Is this either increasing or decreasing the entire time? Is the inverse a function? Well, if we take a look, starting left to right, we're increasing, 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 and then what happens? Now our y values are going down, so we're decreasing. And then what happens again? We're increasing again. So since we're kind of flip-flopping, we're going from increasing to decreasing to increasing, we could go ahead and say, no, it is not, the inverse is not a function. Now, the other way we could test is if we held a horizontal line, so held our pencil horizontally, we could see that it would cross the graph at 3 points if I hold my horizontal line around here. So therefore, the inverse is not a function. So how would we describe it? Well, we would go ahead and say, no, the inverse is not a function. Reason, it's not increasing nor decreasing the entire time. It's flip-flopping, right? And so that means it's not one-to-one, and it fails the horizontal line test. So one last thing I want to reiterate here is this was just to determine if the inverse was a function, okay? Not whether or not it has an inverse, because all relations have an inverse, but the inverse is not always a function, so we have to keep that in mind. Okay, now we're going to get some practice sketching the graph of the inverse, and then we'll determine if the inverse is a function. So we're given the blue graph in our notes. How did I get the green graph? The first thing I want to do is I want to identify some points on my blue graph. So I notice here I have the point 1, 1, I have the point -1, -3, and I also have the point -3, 1. Well, remember about inverses, all I have to do is switch my x and y's. So if I'm able to create my table for my blue graph, all I have to do to graph my inverse is flip-flop my x and y's. So instead of the point 1, 1, well, I still have the point 1, 1, but I switched the x and y's. But instead of the point -1, -3, I'm going to plot -3, -1. And instead of the point -3, 1, we plot the point 1, -3. So we go ahead and we plot those. So there's 1, 1, there's -3, -1, and there is 1, -3. And now we can go ahead and draw in our sideways parabola. So what we should note is, 1, the graph should have the same shape. There's just a little transformation of it, okay? And another thing that we should really talk about with inverses is that inverses are symmetric about the line y equals x. So if I were to fold my graph along this line, my blue and my green graph would match up. Both pieces would. Now the last thing we have to determine is this function, the green, is the inverse a function? So is green a function? And there's kind of two ways we can talk about it. Okay, hopefully you recognize, no, f inverse is not a function. The inverse is not a function. But how do we know? Well, we could use the horizontal line test on blue. So if I use the horizontal line test on blue, so now I'm going across and I'm strictly focusing on blue. Blue fails the horizontal line test. That's how I know green is not a function. But I could also use a test on my green. If I was given green and I wanted to determine if green was a function, I could then use my vertical line test on green to determine if it's a function. Now this green fails the vertical line test, therefore green is not a function. So notice that over here, vertical line test for VLT, and I use the horizontal line test on blue to determine if the inverse is a function or not. That can be confusing. We'll definitely go over it in class. Now we're going to talk about proving whether two relations are inverses of one another, or two functions are inverses of one another. So we're going to use composition of inverse functions property, which says if f is a one-to-one function, then f inverse is the inverse function of f if and only if when we take f inverse and plug it into f, so this is our composition, so f of f inverse of x equals x. So when it simplifies, we get x, okay? And then the reverse. If I take f and I compose it within f inverse, so f inverse of f of x equals x. So let's look at an example of how this works out. Okay, so I want to use composition of functions to prove that these two equations, these two functions are inverses of one another. So I need to show that when I take one equation and plug it into the other, I get down to x, all right? So my first scenario is f of, make sure that that's an open circle that represents composition of f inverse of x, okay? So I want to make sure that this equals x. So I'm going to take this equation here and plug it into the x in the function f, in the equation f, okay? So all I did was substitute. Instead of x here, we now take 3x minus 6. And now we just have to simplify and clean it up. So I'm going to distribute the 1/3 to 3x, and that's where we get x. 1/3 times -6 gives me -2, and we still have the 2. And now what we should notice is the 2's cancel, so I am just left with x, and that's what I needed. So now I do a little check mark, and now I have to show that the other composition, the reverse of that, also gets me down to x. So now I'm going to take f, and I'm going to plug it into the x in f inverse. So instead of x here, I'm going to put 1/3 x plus 2, so you can kind of see that substitution. Now we just carry out the operation. So distribute the 3, that's where we get x. 3 times 2 is 6, and we can't forget about subtracting 6. The 6's cancel, and we are down to just x, so I can do my check mark. So then our conclusion is, since the composition of both of these equals x, f and f inverse are inverses of one another. The last thing we're going to do is actually find the inverse equation given an equation to begin with. So if you look over here on the right, it talks about the steps. All right, so step number 1, instead of f of x notation, we're going to substitute for y. So if you look at this equation here, f of x equals 3x plus 8. Step 1, I make it y equals 3x plus 8. Step 2, what's so special about inverses? Remember, we switch x and y. So now, instead of y equals 3x plus 8, I have x equals 3y plus 8. Now what we want to do is we want to solve for y in terms of x. So I want to get y all by itself. So I'm going to subtract 8, and then I will divide by 3. And you can see what we have here. And finally, the last step, we don't want to keep our answer in terms of y because we didn't have a y to begin. The last thing we do is we substitute f inverse of x for y. So instead of y equals x minus 8 over 3, we have f inverse of x equals x minus 8 over 3. We could break it up this way, but there's no need to. So here is our final answer. If you have any questions, make sure to ask in class.